Okay, so let's dive right in. When you hear GPS, you almost certainly think of maps, right? Navigation in your car or on your phone.
Sure, that's the everyday use case for most people.
But for the huge digital infrastructure that, basically runs our modern world,
Mhm.
its most vital function isn't navigation at all, it's timing.
Exactly. Incredibly precise timing. We're talking nanoseconds. And today we're looking at a piece of hardware, the Thor F1 GPS system, that shows you exactly how that's achieved.
So that precise clock signal comes from a satellite, which sounds fragile. How do you get it where it needs to go?
Well, that's the core problem. It is a fragile radio signal. If you try to send it down a traditional coax cable for any real distance, the noise just
And the
skyrockets.
signal degrades.
Completely. Those nanosecond tolerances just vanish. So the solution is to turn to fiber optics. You basically convert that radio signal into a pulse of light.
So you're turning radio waves into light just to move them. What exactly are we moving? What signals are we talking about here? We're talking about the core GPS signals, L1, which is the standard civilian one, and L2, which is for more specialized uses.
Okay.
But the crucial thing to know is that this system is engineered to handle signals from all the major global constellations: GPS, Galileo, GLONASS.
So it's future-proof. It doesn't matter which system is dominant.
Precisely.
And the practical application for this, who needs timing this perfect? Who's the major client?
The main one, without a doubt, is synchronizing cellular base stations.
5G and 4G networks.
Exactly. If the cell towers aren't perfectly synchronized, two big things happen. Your call drops when you move between towers, and the network's capacity just collapses.
So systems like DS, WiMAX, LTE, they all rely on this flawless clock.
They absolutely depend on it.
Okay, so if 5G needs this perfect timing, what are the limits? RF signals die off so fast, but fiber really changes that whole equation.
It completely changes the game. The flexibility here is incredible. The system is specified to work from a short 1-meter hop all the way up to 50 kilometers.
50 kilometers, wow.
50. Because the signal is light, distance becomes so much less of a factor for signal degradation than it ever was with copper.
And the architecture itself, it seems designed for massive expansion, not just one simple link.
Correct. It supports simple point-to-point, sure, but it's built for scale. You can use optical splitters to turn it into a point-to-multi-point setup.
A star configuration.
Yeah, you can do up to a 1 by 32 split. So a single antenna feed can service dozens of pieces of equipment across a campus or a small city.
And you can even cascade them.
You can. Engineers can chain receivers using smaller splitters, getting, say, 6 GPS outputs right where they need them. It's very flexible.
When we're talking about critical infrastructure like this, durability is it's non-negotiable. How is the system engineered to not fail?
This is where you see the really pragmatic design choices. The transmitter often sits outdoors near the antenna, right? So it's in a NEMA 4 enclosure.
Which means it's waterproof.
Fully waterproof. It can handle extreme weather. Then the receiver is a standard 19-inch rack mount unit, so it slots right into a data center.
And the power.
Dual redundant power supplies. In a mission-critical system, you just can't have a single point of failure like a power supply. If one goes down, the other takes over instantly.
So if something does go wrong on a 50-kilometer link, how do technicians find the problem without just guessing for hours?
They don't have to guess. Both units have these small, built-in LCD displays.
Well, that's smart.
It's a lifesaver for field techs. The transmitter shows you the incoming RF signal strength and the optical power it's putting out. The receiver shows the incoming light level and the outgoing RF level.
So you can see immediately where the breakdown is.
Instantly. It prevents so many costly and time-consuming truck rolls.
So to pull this all together, this equipment is really a perfect example of how we protect this invisible but essential timing signal.
It is.
It takes a fragile radio pulse and basically hardens it into a reliable long-haul optical clock, which is what lets our 5G networks and data centers even work.
And the key to that is preserving the signal's integrity from the very beginning. That's why it uses a low-noise amplifier, an LNA.
To clean up the RF signal before it even gets converted to light.
You got it. It ensures the minimum amount of noise gets added along the way. But, connecting this to the bigger picture,
Go on.
we focused on cellular. But what other kinds of infrastructure depend on this level of hyper-accurate, low-noise timing? Think about stock trading, power grids, maybe automated vehicle control. What are the systemic consequences when that timing is lost?
That's a very sobering thought and a risk factor worth understanding.